Hi, I'm Norman Wahlberger. I'm a pure mathematician at the University of New South Wales, and this is the beginning of a new series on hyperbolic geometry. Now, I've been looking forward to this for quite a long time now, because this is an opportunity for me to really revolutionize this subject, to pick it up and put it in a new place. And it's very exciting, and it's very beautiful new approach to this subject. I think you're going to really enjoy it. And so this talk today is going to be a little bit of an introduction. I want to frame the general direction that I want to go in. I want to give you an idea of what you're in for. A big treat. Okay, so this new series is going to present a simpler, more logical, more general, and more beautiful approach to hyperbolic geometry. Okay, here's me. I'm Norman Wahlberger. I'm an associate professor at the University of New South Wales, which is in Sydney, Australia. My YouTube channel is NJ Wahlberger, and there you may already find lots of other series that I've made or am making. Most of them are ongoing. So Wild Trig series on rational trigonometry, which will be very closely connected to this series. Wild LinAlg on linear algebra. Math Foundations, trying to fix the mess that modern mathematics is currently in. Algebraic Topology. Math History. And the occasional seminar series. Alright, so let's begin by having an overview of the usual story that you usually meet in most hyperbolic geometry courses. Hyperbolic geometry is taught in many places around the world. Many courses at universities offer this. There are many books on the subject, and there are lots of videos you can watch on YouTube and other places. The usual story is a historical one, and it treads a rather well-trodden path, almost invariably starting with Euclid's parallel postulate, and eventually getting around to the remarkable insights of Bolyai and Lobachevsky, and also Gauss. Then further amplified and explained by Beltrami, Klein, Poincaré, and then connections with 20th century figures such as Coxeter, the Dutch artist Escher, Thurston and his program for understanding three manifolds, and perhaps Einstein's special theory of relativity. The usual story is framed with the assumption, almost always unchallenged, that the right ways of thinking about geometry are in terms of distance and angle. Now, if you've been watching any of my rational trigonometry series, you will know that distance and angle are not the right concepts to study geometry, and they almost doom you to misunderstanding the subject. That's doubly the case here in hyperbolic geometry. So it will turn out that an approach via distance and angle really dooms you to misunderstanding the subject. You have no hope of understanding the subject properly, to be quite honest, if you think about it this way. So, but anyway, that's what's usually done. And then there are various models or pictures in which hyperbolic geometry is framed. Here's a Poincaré disk model, which takes place in the interior of a disk. And the lines in this geometry are arcs of circles that are rather carefully positioned so that they're at right angles to the boundary circle. And one measures distances and angles and tries to understand certain things. There's an upper half plane model, which is much like this one, except that all the action takes place above a line in the plane. And the geodesics, or the lines in this geometry, are also half circles. There's another quite different model called the Beltrami-Klein, or projective model, which also takes place in the interior of a disk, but now the straight lines really are straight lines, but the angles aren't quite the same angles as they are in the Euclidean case as they are over here in the Poincaré disk model. There are a few other models too. There's some hyperbolic model having to do with three-dimensional space. But in most books, you treat one or more of these two-dimensional models. While those models aren't that bad, the formulas that go with them are very complicated, and they look sort of like this. In fact, these formulas are all taken from the subject. These are standard formulas in the standard approach to the subject. Okay, we're not going to explain them here. Okay. In fact, these formulas are not going to appear almost at all in our course. We're going to replace these rather complicated formulas with a lot simpler formulas, which are, however, more powerful than these ones. So it will turn out that our more powerful formulas imply all of these formulas. Okay, but these formulas do not imply our formulas, because our formulas are more powerful and much better. But anyway, here's what you have to do if you're going to study hyperbolic geometry in the standard way that you can learn in most universities today in the year 2011. Okay, there's logs, there's cosines, there's hyperbolic functions, there's lots of square roots, there's tans, there's exponentials, there's formulas with lots of trig things. There's some differential geometry usually thrown in. It's very complicated. And it's no wonder that it's considered a rather exotic subject, only suitable for advanced undergraduates. What a sad mistake that is. Hyperbolic geometry is such a beautiful and simple and elegant subject. It's something that everybody should know something about. It is really so simple and beautiful. And I hope that I'm going to get a little bit of that across to you in this course. So I'm going to present you with a completely new story of hyperbolic geometry, a new vision of what this subject is, and what directions it goes, and what form it takes. And very roughly, some of the ingredients of this new story are, first of all, Apollonius, great ancient Greek mathematician, who was an expert on conics, and who discovered some very fundamental and important and beautiful things about conics, which sadly are almost not at all seen in schools these days. But nevertheless, they turn out to be just what we need to do hyperbolic geometry in the right way. So certain notions called polarity, an idea called cross ratio, projective geometry, which is intimately connected with these things. And then the work of Bolyai and Lobachevsky and Gauss, still very important. Beltrami, yes. Einstein and Minkowski's special theory of relativity. Connections become much more important. But I suppose the really defining new characteristic is that we're adopting the point of view of rational trigonometry. And that's what opens the doors for us. That's what allows us to venture into this broad, beautiful new arena. Okay. Without rational trigonometry and the basic framework there, it's hard to find the door. But with rational trigonometry, it opens easily and everything is beautiful. So the kinds of pictures that we end up with is something like this. We're still going to have a circle. Our lines are going to be straight lines, just like the ones in the Beltrami-Klein projective model. Except that we're not going to be just working inside. We're going to be working inside and on and also outside the disk. This is in fact what classical hyperbolic geometries used to do about 100 years ago, before the subject was kind of hijacked by others and taken in different directions. So I suppose the essence of our approach from this planar point of view is that we're looking at the projective plane. I'll explain eventually what that is, plus a distinguished circle. So hyperbolic geometry for us will be what we get when we combine projective geometry of the simplest kind with the simplest conic. And instead of distance and angle, we're going to work with quadrants and spread. Analogous to the Euclidean quadrants and spread, but kind of projectivized versions of those measurements. And quadrants will typically be denoted by a little q, with a little rectangle like that to denote where it is. And the spread between two lines usually denoted by a capital S and denoted by a little straight line segment like that. And of course our geometry is going to have some formulas. So there will be some formulas, but they are much nicer than the other ones. much nicer than the classical formulas. And here's what they look like. Well, here's what a lot of them look like, the most important ones, in fact. On this page are probably the 7 most important formulas, and eventually we'll explain all of these formulas and talk about them and their importance and significance. They're all related in nice ways. But the point is that they're all algebraic formulas. There is no exponentials, there's no absolute values, there's no square roots, there's no transcendental functions like sines, cosines, or hyperbolic tans, or anything like that. They're quadratic equations in any one of the variables. So it turns out that high school algebra is all what you need to be able to work with the formulas in this subject. It's 1,000 times easier than the other one, really. Because a consequence of that is we're going to be able to make calculations without calculators. We'll just be able to make calculations by hand. And the answers that we're going to get are actually correct answers rather than just approximations. Ordinary classical hyperbolic geometry, it's very hard to make calculations which are actually correct. Easy enough to make approximate calculations, but correct calculations is a different story. There's a very important difference between this subject and the previous one. So the advantages of this new hyperbolic geometry, whose name, by the way, will be universal hyperbolic geometry. The advantages are it's simpler, it's more logical, it's more general. It's simpler in a lot of ways, but in particular the lines are straight rather than arcs of circles. That's a lot simpler. The formulas, as we've seen, are algebraic or polynomial. Only high school algebra is needed. No calculus or transcendental functions are required. So it's an elementary subject. It's more logical. No real numbers are required, real numbers in quotes. Modern mathematics has serious logical problems with real numbers that are usually swept under the carpet and ignored. But there are very serious difficulties, which most senior mathematicians are aware of, but they probably don't really want to admit it. Anyway, we don't work with real numbers. We work with much more natural framework of rational numbers, which is where mathematics really ought to take place. There are no axioms anywhere. We're not interested in any unsubstantiated assumptions. There's no circular or hyperbolic functions. So we don't have to worry about the fact that functions like cosine and sine and tan are very often not defined properly at all. It's very hard to, in fact, find places where there's a good, consistent theory of the circular functions written down with complete proofs. Most calculus books, most high school books always put all that under the carpet, pretending that it's not there. We're going to avoid all of that. Why is our subject more general? Because it works over a general field. In particular, it works over the rational numbers, and it works over finite fields, it works over the complex numbers, it works over any field that we like. It's a very general framework. The formulas extend outside the disk, not just inside. And it turns out that our formulas also unify the 2 standard non-Euclidean geometries. One of them is the hyperbolic geometry, and the other one is elliptic or spherical geometry. So it turns out that these 2 geometries come together in this framework, and the basic formulas are ultimately identical for both subjects. It's a big unification. But there's one advantage that's perhaps even more important than these 3. And that is that it's much more beautiful. This subject is really beautiful. Now, I have done research work in lots of different areas. Over the years, I've studied number theory and Lie theory and representation theory, and I've done some harmonic analysis and some mathematical physics and some combinatorics. And I can honestly say that hyperbolic geometry is more beautiful than any of those subjects. It is an incredibly beautiful subject, and it sits right in the heart of mathematics. It's no surprise at all to me that Einstein's theory of relativity, which is one of the most remarkable developments of 20th century maths and physics, really is very close to hyperbolic geometry. It's the way God wants to express the beauty of the natural world. In terms of specific advantages, well, it certainly connects with special relativity better, as we'll see. Computations are faster and more accurate, as we'll see. The whole subject of hyperbolic triangle geometry comes into focus for us. In classical hyperbolic geometry, triangle geometry is a relatively understated or underdeveloped subject. There's good reasons for that, but we're going to be able to overcome those obstacles, and it turns out this is an incredibly rich and vibrant subject. Fascinating combinatorial aspects come into play because we're able to do hyperbolic geometry consistently over finite fields. So you can start to count things, and it's very lovely. The group theory that underlies hyperbolic geometry is richer. And there's another kind of symmetry theory called hypergroup theory, which comes into play and is also very interesting. And we'll see that we're going to get new insights into algebraic geometry. So lots of advantages for us. So let me say a few words about the course. It's mostly self-contained. Occasionally I'm going to ask you to check out one of my other videos in one of my other series to bone up on some particular subject. But other than that, things are going to be pretty well self-contained. So we're going to start from an elementary level, and we're going to work slowly and methodically, and it's never going to get too complicated. The intended audience is, well, college math students certainly, high school math teachers, retired engineers or scientists or other people who are otherwise somewhat mathematically inclined. Bright high school students will be able to follow it. And otherwise generally interested lay people who have an ability for mathematics or an interest in it. What do you need? Well, you're going to need an internet connection. You'll need a straight edge and a compass, because it's going to be fun and useful to make actual explicit diagrams, to verify statements, to illustrate a lot of the theorems. You are going to require a certain amount of algebraic competence. You don't have to be a genius, but you can't be afraid of some formulas. So here's a good test for you. Okay, have a look at this little problem. Suppose that I ask you to start from this relation. This is a relation between two variables q and r. It's actually a very important relation, and from that I want you to deduce that r is either equal to 0 or 4 times q times 1 minus q. In other words, I'm asking you to solve this for r. Now, if that sounds completely impossible to you, then this course probably isn't for you. Or if you're not interested in doing any work and you just want me to explain everything, it's probably also not a good way of spending your time. However, if you look at this question and say, all right, wait a minute, I'll get a piece of paper, I'm going to get my pen, I'm going to write that down, I'm going to manipulate it, I'm going to see if I can do that. And if after 10, 15 minutes or half an hour you're able to get this result, then that's what we want. That's the level, roughly, of algebraic expertise that you need. You've got to be able to solve a quadratic equation and not be afraid of some variables. So I want you to be willing to work a little bit. I'm going to give you some problems to do. I expect you to work on them. And you probably need an open mind, especially if you're a graduate student or maybe a professional mathematician. This is a new way of thinking about not just geometry, but also other things too. Open mind helps a lot. And one more thing that's not exactly required, but recommended, is a computer geometry program. The one that I use most of the time is Geometer's Sketchpad, which I'll just call GSP. That's a commercially available program. Many of you will know that it's used in high schools in the United States, for example, quite extensively. It's a very beautiful program. But there are others which are also very lovely. I mentioned Cabri, Cinderella, GeoGebra, and this one here, CAR, which has the advantage that it's free. So these programs allow you to work on a computer and to draw nice diagrams and to manipulate things and see how certain constructions change as you manipulate control points. So that's going to be a very good additional tool that will help you. The lectures are going to be roughly 30 to 40 minutes long. Eventually I hope to post some notes that go along with the lectures somewhere. And I'll often give you some practice problems and occasionally some research problems to work on. 100 years ago, geometry was a much more open-ended subject, and high school teachers and amateurs played a bigger role in contributing to the theory. I'd like to see a bit of a return to those days. So one of my aims in this series is to encourage people to make investigations and possibly discoveries in geometry. And with this series, you are really in an enviable, novel position, and that I'm actually going to put you in the forefront of mathematical research. And with a bit of work and a bit of enterprise, enthusiasm, you will be able to discover new things. So I hope that many of you will end up sharing your understandings with me and others too. That's what I would really like to see. Alright, so we've got a great adventure ahead of us, and it is an intellectual adventure. It's very exciting, and I'm really looking forward to it. So I wish you all the best. Good luck to you. Next time we're going to start with the course proper, and we're going to start by going back to the ancient Greeks, where I claim hyperbolic geometry has its true origins, in the work of Apollonius. So I'll see you then. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.